All right, so we're going to be now talking about the area of a region. And before I begin talking about the procedure, I just wanted to give you a very brief, and when I mean very brief, a very brief history lesson on area. So, for a very long time, especially in Euclidean geometry, the most basic and simple type of area computation is the area of a rectangle. Because as we know, the area of a rectangle is defined as base times the height. So the area of a rectangle is defined as base times height. So we know that since like middle school. Now, the area of other shapes and polygons and figures, at least in the beginning of, like in pre-modern modern times, in ancient times, was defined in terms of rectangles. So for example, the area of a triangle, if you wanted to locate the area of some triangle, what you would do is you would create a rectangle that would encompass that triangle, sort of like this. Yeah, kind of like this. And what you will do is you will measure the height of the triangle, and the height of the triangle is going to be equal to this side length. So I'm going to call them x. And then the base of the triangle, we already know because look at this side, that's how we capture the base. So I'll call that b. I'm going to call this x as well. Let me call it xh. And notice now that what you end up having is when you end up doing this and you compute it, you have that the area of the triangle is 1/2 the base times the height of the rectangle. So if you have a rectangle and you take half of that, you get the area of a triangle, and this makes sense. If you draw a rectangle, then look how easily I can make a triangle in there. I have two of them now. So I have triangle 1 and triangle 2. The area of triangle 1 is half of the area of the rectangle, and the area of rectangle 2 is half the area of the rectangle. When you add them up, you get the full area of the rectangle. So that makes a lot of sense. The same is true for figures such as a parallelogram. You know, you can make a triangle going in this direction and define it by using rectangles as well. Well, in fact, once you know the area of a triangle, which we got from here, then you can figure out these areas as well because these are just triangles. Same thing goes for like a hexagon. So let's say you have a hexagon which looks like this, sorta. Then what you can do here, it's an ugly hexagon. Let me do it again. So with a hexagon, what you could do is you also make triangles because now we know how to find the area of triangles. So you could do it like this. So you have 1, 2, 3, 4, 5, 6 triangles. So when you find the area of each of them individually and you add them up, you get the area of the whole hexagon. And for many other polygonic figures, you could do the same thing. Like if you have some figure that kind of looks like this. Right? If you have some figure that looks like this, then if you make triangles and you get the area of these triangles, then you could find the area of the whole polygon. Now, the one that's of interest that I really like was the circle. So to get the area of a circle, today we have a very nice formula, but to actually get this area, you have to actually estimate it using polygons. So you may use you may begin with like let's say like a big rectangle, right? Yeah. So you may begin with like a rectangle, but notice that this rectangle has x's area here, no displaces, so that doesn't really work. Well, since that didn't work, you begin to estimate something a little bit smaller, like and you could do this by using many techniques. So one of the techniques that's used is to create triangles on the inside. So you could have created a triangle going from here to here, right? And then you create another one on the inside. So there are many ways of doing this, but this is how the area of a circle was found, by inscribing it in many polygonal shapes of increasing size. So we began with a rectangle that has 4 sides. Then the next logical way to enclose it will be with a pentagon, which has 5 sides, like this. Right, and now we have less area that's being taken up by empty spaces, and then you go with a hexagon now, and then you go with a hectagon, and so on, and then you keep increasing the number of sides of your polygon until what you have is nearly a circle. So this is also a limiting process, and from there, to make a long story short, we get the so-called area of the circle, and the same process of using a polygonal figure to find the area is what we're going to use to find the area under curves. Like, for example, if somebody gives you a curve that looks like this, and they ask you, okay, find the area under the curve from A to B, meaning this area right here, how would you find it? Or somebody gives you this picture, something that looks like this, and they ask you, okay, find the area under the curve from A to B here. That will be this area right here. How do you find that? So we have techniques of actually doing this. So before beginning, let me just draw a quick picture, and we'll talk a little bit about this picture. We'll find the area of it using a specific figure. Let me just draw this. So we have the following figure, and these intervals are 2 over 5, or 5, 6 over 5, 8 over 5, and 10 over 5. These 0 down here, and then you have 1, 2, 3, 4, and up here 5. And then we're going down like this. Okay, so this is the sketch of the function f of x is equal to negative x squared plus 5. That's a vertex. It has a y-intercept at 5. It's a parabola going down from left to right. Now, if somebody asked us to find the area under this curve from the interval 0 to 10 over 5, how could we go about this? Okay, how could we go about this? So what we do here is we make rectangles. So I'm going to talk a little bit about this. So if I make a rectangle here, right, let's say I make a rectangle in this, let me just redraw this, this line, because it's not too good, it's too flat. So that's a little better. Okay, so we're gonna make rectangles. So let's say I have a rectangle that goes up to the line and then left. Another one that goes up to the graph of the function, then left. Up to the graph of the function, then left. Up and left again. And finally, let's say that this up here and left again. Okay? What happens here? Well, I'm looking for this area on the inside. And if I find the area of each of these rectangles, I get an approximation for the total area under that black curve. But the issue that I'll be facing is that I have this open spaces here that are unaccounted for. Okay, so that's one of the issues that I'll be facing. I have those open spaces that are unaccounted for, but the good thing is that I do get an approximation for this that's easy to compute. How do I know that this is easy to compute? Well, we know that the area of a rectangle is base times height, and we have a way of figuring out the height of these rectangles, and we have a way of figuring out the width of the rectangles. How do we figure out this height? Well, notice that I picked the height to be at this endpoints, 2 over 5, 4 over 5, 6 over 5, and I set to for each one of them that we go up to the graph. So there's a point here that corresponds to an output value of this function. Namely, if you plug in, let's say, 2 over 5 into the function, then you get the height at 2 over 5. So if you were to do this, you get the value of this point right up here, which means that you get the height, because the height will correspond now to that y value. The width, we can see that is 2/5, because from here to here is 2/5, from here to here is also 2/5, because if you add 2/5 to 2/5, you get 4 over 5. If you add 2/5 to 4 over 6, you get 6 over 5. If you add 2/5 to 6 over 5, you get 8 over 5. And if you add 2/5 to 8 over 5, you get 10/5. So the width is 2 over 5. The height is given by this function up here. So what do we have? We have that the right, what I'm going to call the right endpoints of the triangle, of the rectangles, of these 5 intervals, intervals 1, 2, 3, 4, 5, are 2 over 5 times I, where I is equal to 1, 2, 3, 4, and 5. Why is I equal to 1, 2, 3, 4, and 5? Well, think about it. When I is equal to 1, 1 times 2 over 5 is 2 over 5. That gives me the first right endpoint. When I is equal to 2, 2 over 5 times 2 is equal to 4 over 5. That gives me the second right endpoint. When I is equal to 3, you get 2 times 3 equals 6. So you get 6 over 5. You get the third one. So this allows me to get all of the endpoints. This is a nice way of writing all of the endpoints if I is equal to any of these values. Now, I just mentioned that the width of each rectangle is 2 over 5. So what is the area? The area is going to be the height times the width. Now, how do I figure out the height? Again, the height is going to be the function evaluated at each of the endpoints. And now I know a way of figuring out the endpoints is 2 over 5 times I. So what we have here is the following. We have the intervals. We have 5 of them again. We have 1, 2, 3, 4, 5 of them, 5 rectangles. So we can find the area of each rectangle on each interval and add them up. So the intervals are 0 to 2 over 5, 2 over 5 to 4 over 5, 4 over 5 to 6 over 5, 6 over 5 to 8 over 5. Notice that the endpoints are included. And 8 over 5 to 10 over 5. Okay, so these are the 5 intervals. And to get the height of the rectangles, we simply evaluate the function f that's given at each of the right endpoints. Endpoints of these intervals. Okay, so what we really are doing is to get the, for example, to get the area of this first rectangle. The area, let's call it A1 of that first rectangle is going to be base times height. Well, the base, I know the width is 2/5 times the height. Well, the height is f of 2/5 because that's the right endpoint. For the second rectangle, let's call it A2. Again, it's base times height. The base is still 2/5, but now the right endpoint of the second interval is not 2/5, it's 4/5. So this is f of 4/5, whatever that is equal to. I'll multiply it times 2/5 and I'm going to get the area. A3 follows a similar pattern. It's base times height. Again, 2/5 is not changing. That's the base for every single rectangle in this interval has a width of 2/5 because that's the way that we broke it down. But now the height changes because the endpoint changes. Instead of 4/5, it's now 6/5 because again that is the third interval. The right endpoint is 6/5, and so on. You know, you could go to A4, A5. So again, we have base times height. That's equal to 2/5 times f of 8/5, and finally we have 2/5 times f of 10/5. Now, the way that I'm writing it here, you know, it's the long way of doing it. Once you get all of these, you could add them up. You do A1 plus A2 plus all the way to A5, and you get what the area is, the estimation or the approximate area is under the curve. Now, using sigma summation and sigma notation, everything that I wrote up here is equal to the following. It is equal to the sum I equals 1 to 5, which is the reason why I wrote it up here, 1 to 5 of what? Well, again, it's base times height, or the width times the height. So what is the height? The height is given by f of what? F of 2/5 times I. Because notice, each right endpoint is 2/5 times I, where I is equal to 1, 2, 3, 4, 5. You know, 1, 2, we did that. And the height is simply 2/5. So it's going to be the sum from I equals 1 to 5 of the height times the width. Okay? But notice that this is equal to, again, what is f? If we go back to the beginning of the problem, f is negative x squared plus 5. So this is equal to, let me write it up here, f of x is equal to negative x squared plus 5. So if you substitute now 2/5i into negative x squared, we get the sum from I equals 1 to 5 of negative 2/5i squared plus 5 times 2/5. And now this is the height, and this is still the width. But this is equal to the sum from I equals 1 to 5, and you know this portion in here is going to be negative 4/5i squared. Negative 4/5i squared plus 5 times 2/5 times 2/5. And now we can actually complete the sum. You could multiply in first if you want to, or you could take out the 2/5 completely. If you do choose to multiply it in, then what you have is the following. You have the sum from I equals 1 to 5 of, when you multiply it in, you get 2 times 5 times negative 4/5i is negative 8 over 25 I squared plus the 5's cancel out, so plus 2. And now what you have here is this particular sum, and then all you have to do now is substitute the values from 1 to 5 here, and then add them all up together, and you'll get a solution. So if we were to do that, we'll have negative 8 over 25, let's say, times 1 plus 2 plus negative 8 times 2 squared over 25 plus 2 plus all the way up to negative 8 times 5 squared over 25 plus 2. Okay, and then when you actually compute this sum, you will get some cancellation, and you will get the result of the actual sum. Okay, so this is how you do a right sum. This is one way of doing the sum. Now another way of doing this sum for the same area, notice that this is an approximation again. I still have these open spaces that are unaccounted for. So another way of doing this sum is to do the left sum. So this is called a right sum. So what we did is called a right sum, because we used the right endpoint of the rectangles. So what we could have done a left sum, and for a left sum, for the same picture, we have 2 over 5, 4 over 5, 6 over 5, 8 over 5, 10 over 5, 3, 4, 5. And this kind of look like this. Again, not to scale. For a left sum now, what we're doing is we're focusing on the height of the rectangles being given by the left side of the interval. Instead of, so before we were using the right side to get the height, now I'm going to use the left side. So on the interval 0 to 2 over 5, the height is given by the point x equals 0. So there's going to be, we're going to go from 0 all the way to 5, then across, and then down. And then same thing for 2 over 5. We're going to go up, then across, and then down. And for 4 over 5, we're going to go up to the graph, then across, and then down. Then back up to the graph, across, and then down, and finally up and across and then down. Now notice that here we will have an overestimation. So in the other one we had an underestimation. In this one we're going to have an overestimation, because these pieces of area that we get on the rectangles are not underneath the curve for which you want to get the area for. So if we get the left approximation, we're going to get an overestimation. So we had an underestimation and an overestimation, and the actual area will be between this underestimation and this overestimation. Okay, so let's say if this is the area, then it's going to be less than or equal to the left sum. I'm going to just call LS for now, and it's going to be greater than or equal to the right sum, which I'll call RS for now. So it's going to be trapped in between them. Now, because we are working with the same picture, the width is still the same. The width is still 2 over 5. But now the height is not given by 2 over 5i, because we are not looking at the right endpoint, we're looking at the left endpoint. It is actually given by 2 over 5 times I minus 1 instead of I. The reason for this is quite simple. If you look at it, the first term is no longer 2 over 5, it's 0. So the first term, when I is equal to 1, we have to get 0. So if I is equal to 1, 1 minus 1 is 0, and 0 times 2 over 5 is 0. So that's why we do I minus 1 instead of I. If I is equal to 2, then you get 2 minus 1, which is 1. And then we do get 2 over 5, and then 4 over 5, and 6 over 5, and so on. So for the left, for the left sum, the left right point is given by your value times 1 minus I. So let's call that value k. So it's going to be k times I minus 1 for the left sum. And for the right sum is going to be k times I. Okay, so let's finish up this problem. So now that we have a way of determining the height and the width, it's again a matter of putting it together. So we have a sum from I equals now 1 to 5 again. So this remains the same, the endpoints, the upper bound and lower bound. But now, notice that this gives us the height, but the height is given by our function, so this is the input. So it's going to be 2 over 5 times I minus 1 inside of f times 2 over 5. Okay, so this is giving us the height. So this is the height, and this is the width. Okay, so this is really not the height. This is I call it the height because it's going to be equal, but the correct term for this will be just the right endpoint. It's misleading if I call that the height, but this is the input for the height, to get the height. Anyway, when we do this, you get the sum from I equals 1 to 5, and then if you plug in this into f, what you get is negative 2 over 5 times I minus 1 squared, squared, what's it, plus 5, right, times 2 over 5, which is the width. Okay, now if you actually do this, I can say, I could multiply this in square. If you actually do this, you will get a solution. So you could simplify this, you could then square it, and then you'll see what the solution is. But this is the so-called right endpoint. And it turns out that the area of this figure is trapped between them. I'm going to end this part right here with these formulas because this is the process. Everything else is just plugging in. So you're going to plug in and then add everything up. So basically you're going to plug in 1, then 2, then 3, do the multiplication and add. But I'm going to show you using Maple how this is going to look before we go on to the rest of the lecture.